Okay, everybody. So in this lesson here, we're going to start talking about horizontal and vertical stretches of our functions here. Okay, so a stretch, or like it says here, a stretch or a dilation, another word for it, it changes the shape of the graph, but not its orientation. Now, when I say shape of the graph, what I mean by that is like a parabola is still going to stay a parabola, but maybe what happens to it is it gets wider, right? Or it gets narrower or something like this. So we're not changing what the function is, but we're changing the look of it a little bit. And here's how we do it. And I want to make sure that you understand the notation up here. Let's take a look at well, here I'll highlight it. Let's take a look at this little bit up here. So what's happening here? Well, let's apply the order of operations. So first of all, we've got this function here, f of x. This is our old function. And we're going to create a brand new function with it by doing something to the old one. Now, we go inside the parentheses here and notice that the first thing that we're doing is multiplying the x by this value b. Okay, that is changing the x. So b is giving us a horizontal. There's something horizontal going on here. And I'll tell you right now, it's a horizontal stretch. And we'll explain that in a little bit more here. But I just want you to catch right now that if it's inside that function right there, it's horizontal. Then f takes what's inside and f creates y coordinates. Okay, f, the function, takes the new value of the independent variable. So I multiplied x by b, got it. Then the function changes that into a y coordinate. And then I've got this a value here that's multiplying now by a y coordinate. So that is going to change things vertically. So that is going to be a vertical stretch. Okay, that's what a is responsible for. So why don't you just catch the rhythm there? B changes the independent variable, changes the x. F changes that result into a y coordinate. A now changes the y coordinate. So let's go through and start talking about the stretches individually here. So we start with our original function, y equals f of x. And what we're going to do is in that function, we're going to replace y with 1 over a y. So for example, we might replace it with 1 over 2y. And I know that looks like we might be making it more complicated to replace the y with a fraction multiplied by y. But here's what's going on here. So what I do is I take that y equals f of x, basically y equals f of x. And when I say replacement, I mean that. I'm literally going to wipe out the y there and put in 1/2 y. And then what I do is we're going to move that 1/2 over by multiplying by 2. Or if you want to think of it, you're dividing both sides by a half. And when I bring that over, now that fraction is this whole number here, this 2. Remember that f of x is the old y coordinate. Going back over to our original function here, f of x is that original y coordinate. And notice that now what I'm doing is I'm multiplying that by 2. So that becomes our vertical stretch. Okay, so that's what you're seeing right here when we write this out. This is a vertical stretch by a factor of a. I'm multiplying the old y coordinate by a, okay, to get my new y coordinate. And in my mapping, my mapping reflects exactly what is going on with the points. So my x comma y is going to be x comma a times y, or in the specific example that we just gave here, every x comma y on the graph is going to be x comma 2y. I'm going to multiply the y coordinate by 2. Now, because this stretch is achieved by multiplying the y coordinate by a value, if I just stop and think for a moment, what number doesn't change when you multiply it by, let's say, a 2? The answer is 0. 0 times 2 is just 0. It doesn't change here. So what that gives us here is our invariant points. Our invariant points are going to lie on the x-axis. These are going to be our x-intercepts. Okay? Now, let's talk about the horizontal stretch. If I start with this original function, y equals f of x, I'm going to replace x with bx. And let's say, for example, that I replace it with 3x. So that means in my original function, Where I've got that x, I'm erasing it, and in its place, I'm going to put 3x. Now, it turns out what that does to the point is it actually causes a stretch of 1 over b times x. And that can be a little bit confusing. And I want to talk about what's going on here. Let's say that you had y equals x squared, okay? Let's say, for example, that I gave you the y coordinate and I wanted you to get the x coordinate. If I wanted you to find out what the x coordinate is, what you would have to do is take the square root of the y, and that would get you x. Now, granted, you're going to have the plus or minus there. So x would equal plus or minus the square root of y. Okay, good. Now let's say that instead of that, I had replaced x with 3x. So now it was 3x squared. But I do the same thing. I give you a y coordinate, and I want to figure out what the x coordinate is. So the first thing I'm going to do is take the square root of the y, plus or minus, and that's going to get me 3x. And now here's the difference. Now, that plus or minus y, that is the same as my old one when I did it originally here. But now my new x coordinate is going to be plus or minus y divided by 3. So what happened here is remember that plus or minus y is the old x coordinate. The new x coordinate is that old one divided by 3. That's what's going on here. So that's why I'm seeing this reciprocal when I look at the mapping. Okay, you don't see that with the vertical transformation, because in the vertical transformation, we are very naturally isolate the y. So we already bring the a value to the other side. And remember, it was 1 over a on the left-hand side, but it became a over 1 on the right. So you naturally want to find the reciprocal of it. But with the horizontal transformation, you don't. We don't isolate x. So you don't necessarily see it. But that's why the stretch is actually by a factor of 1 over b about the y-axis, and we should highlight that. Now, just like the vertical one here, the action here is comes from multiplying the x coordinate by something. So what's the only value that doesn't change when you multiply it by something? 0. And so my invariant points here are going to be when the x coordinate is 0, and that's going to correspond to your y-intercepts. Okay. Now, but I want you to think about what we're doing really quickly. I got one more little thing I want to say about this before we move on. In these cases here, particularly if you look at your mapping, the mapping here, I am either multiplying the y coordinate by something or multiplying the x coordinate by something. Okay. So let's say I'm multiplying by 3. If I multiply the x coordinate here by 3, that's going to move the point this way. But if the point is right here and I multiply the x coordinate by 3, that negative becomes a larger negative further away. Over here, if I've got a point above the x-axis, the x-axis, and I multiply it by, what have I done here? 2, it's going to move it up. If I multiply one down here by 2, it's going to move it away. So when we do these stretches here, we're moving away from or towards an axis. And I would move towards an axis if instead of multiplying by 2, I was multiplying by a half. And the reason I bring that up here, I'm going to just slide up here to this just a little space right here. Let's say that I had an object here, 1, 2, 3, 4, 5, 6, 1, 2. I have this little square right here. Okay. If I performed a horizontal stretch by a factor of 3, a mistake that some people think here is when they look at this, they say, oh, okay, well, it's 1 unit wide, so now it's going to be 3 units wide. And there we go. I've now created this shape that's 3 units wide. It got expanded or stretched by a factor of 3. But that's actually incorrect. Because when you do these stretches, you're not stretching it about the center of the object. We're actually stretching this about the axis. So right here, in this line here, all of the x coordinates are 1. I'm going to multiply all those by 3, and they go out to here. All of these points down here on this side have an x-coordinate of 2. If I multiply that by 3, they go out here to 6. And this is what it looks like when I stretch that horizontally by a factor of 3. This distance becomes 3 times bigger. This distance becomes 3 times bigger. But it sort of looks like it moves the object as well. How I need you to think about this is it's as if the whole plane is a rubber sheet. And when I do the stretch, I'm pulling it away from the y-axis, or I'm pulling it away from the x-axis, or vice versa. I'm pushing everything in. It's like the whole grid is changing. That's how I need you to think about that. So let's take a look at some examples here. So this one says, for the graph of y equals f of x, describe the effect of making the replacement described and give the new function here. Okay, so what we're looking at here in the first one, we're going to replace x with 3x. Now remember what that means. So here we've got the original function. So what we are literally doing here is taking out that x, okay, and replacing it with 3x. Okay, that is what we're doing. That is the new function right there. And we know that this is going to be a horizontal stretch about the y-axis, horizontal, by a factor of 1/3. Okay, because remember, if I was to try to get that x now by itself, to isolate it on the one side of the equation, the last thing that I would need to do here is divide by 3. That becomes that translation here. Here I'm replacing x with 1/4 x, okay, which means that in our function here, y equals f of x, again, I'm going to take out that x, and in its place, I'm going to dump the 1/4 x. And this is going to be a horizontal stretch about the y-axis, y-axis by a factor of, and in this case, again, I'm reciprocating that stretch factor 4. When you get that x by itself, the last thing you're going to do there is reciprocate or divide by 1/4, which is going to be like multiplying by 4. Okay, now I'm going to speed up my notation here a little bit, but I want you to know that you're going to need to write that out on major exams there. So in this next one here, this is going to be y is replaced with 4y. So y equals f of x. I'm going to get rid of that y and put a 4y in its place. But I don't typically leave y with coefficients and other stuff going on here. Usually I isolate the y. So I'm going to divide both sides. And that is significant here. This is going to be now, I'm going to say, a vertical stretch about the x-axis. Okay, and instead of saying by a factor, I'm just going to say by, let's say, 1/4. In this particular case here, I do bring the 4 over. I do the isolation of the y. So when it's over on the other side, when it's in front of the function, that is the stretch factor. I am, okay, if you want to think of it like this, in the original expression, way up here, we have y equals f of x. This is our old function. I am now literally multiplying that old y coordinate by 1/4. So now in question D, we're going to replace y with 1/5 y. Okay, so y with 1/5 y, and replace x with 1/2 x, meaning that we're going to go from y equals f of x to 1/5 y equals f of 1/2 x. Okay, and what we're going to do here is we're just going to identify what's going on here. So what we're seeing here is, I'm just going to shorten this up just a little bit just to get us through this quicker. This is going to be a vertical stretch by a factor of 5 about the x-axis. And this next one's going to be a horizontal stretch by a factor of 2 about the y-axis. Now, you don't want to be shortening that up on a major exam. You want to write that out, the vertical stretch and whatnot. But just for the sake of time right here, I want to do that. In this next question, E, we're going to replace y with negative y. Now that is kind of referring back to a previous lesson. What that refers to is a vertical reflection, okay, right, over the x-axis. And then to replace y with 2y, that's going to be, again, a vertical stretch by a factor of 1/2 about the x-axis. And what we mean by that, remember, is that in order to get that y by itself, when you write that as 2y is equal to f of x, this is your new y coordinate, this is your old one. If you want to know how your new one relates to your old, you got to bring the 2 over. That's going to be division. And here, just for symmetry's sake, really what we're going to get here is a horizontal reflection. And then this is going to be a horizontal stretch, by a factor of 2 about the y-axis. And there you go. Okay, now the next question, and what you're going to see here as we kind of progress through this is that we're really looking at the same thing over and over again, but what we're doing is looking at it kind of from different angles, different perspectives here, but it's the same idea. So we're going to describe how the graphs of the following can be obtained from the graph of y equals f of x, and then we're going to give the correct notation and mapping. Okay, so the transformation here, when I see a 3 in front of the f of x here, and I know that this is the original function, I know that anything outside is vertical, and because I know it's changing the old one, I know that's exactly what it is. So this is a vertical stretch by a factor of 3 about the x-axis. Now that 3 is already moved over and is acting on the old function here. So what I must have done is replaced y with 1/3 y. Okay, and that's going to be what our g of x is referring to as that new y coordinate. Our mapping, well, x comma y, this is both coordinates together. When we talk about replacements, we're talking about them separately, and that's what we're doing in the function. But when we talk about the image point, that's both coordinates together, and we're talking about what's going on in the graph. Nothing's happening to the y, but that is 3y when I multiply that out. Because the transformation, the description, and the mapping are basically saying the same thing. When you describe it, you're describing what you're seeing on the graph. Here, that 5 is being multiplied by the x, which means it's changing the x before the function can turn it into a y coordinate. So this is a horizontal stretch by a factor of, and that's going to be 1/5 about the y-axis. Okay, and it's 1/5 because if I was to try to get x by itself there, to figure out what the x coordinate is, I would have to divide by 5 at the end. In this case here, it's quite straightforward. I am replacing x with 5x, okay, because I can see that immediately in the function. We don't isolate the x, and so what you're seeing in the function is exactly what we replaced it with. And then x comma y is going to become 1/5. 1/5 x comma y. And then here, it parallels what we just did here. This is a horizontal stretch by a factor of, and we just want you to be ready for this, 2 about the y-axis. Okay, I replaced x with 1/2 x. And then my mapping, same sort of thing. X comma y is going to become 2x comma y. Good. Now, usually at this point here in a lesson, this is kind of where I would start to kind of let students really start to do a lot of this on their own here. Write an equation, y equals f of x after the following transformations. This would be a good opportunity if you wanted to just pause for a second, try this on your own, and then come back. Okay, I'm gonna dive in right now, but like I said, it's a good idea to kind of get a sense of, if you see where this is going here. If you want a horizontal stretch about the y-axis by a factor of 2/3. Now, horizontal means I'm going to replace x with something. And remember that I'm always going to replace the x with the reciprocal of the stretch factor I want. So I'm going to replace this with 3/2 x. and that is going to be f of, just like I said, 3/2 x. I'm going to do, for the b here, a reflection in the y-axis. Okay, let's just stop right there. Reflection in the y-axis, that's horizontal, which means I'm replacing x with negative x, followed by a vertical stretch. I'm going to replace y with, well, now what is it? About the x-axis by a factor of 1/5. Okay, so when I do the replacement, I am reciprocating that. The only time that I'm going to flip that back is when I move, after I've done the replacement, when I move that over to isolate the y here. So I'm starting with y equals f of x. My first replacement is going to make this f of negative x. My second replacement is going to make this 5y is equal to f of negative x. And then what I would typically do is bring that 5 over, so I get 1/5 f of negative x. Now, here's another question that I would normally let students work on first before we talked about it. And I would encourage you to do the same thing. Maybe pause the video and have a look at this before we get together and talk about it. But I'm just going to dive right in right now. And one of the reasons why I do this is because this question, when I give you the function, what I want you to notice about it is it's not y equals, I'm anticipating what I'm doing here. It's not y equals or f of x equals just the absolute value of x. There's something more going on here. There's an x minus 1 inside the absolute value, then a minus 4 at the end. So there's a little bit more going on here. So now, how do I do this? So when f of x is stretched vertically about the y-axis by a factor of 1/3, that means I'm going to replace y with 3y. Now, when I build the equation here, I'm going to do some substitution. I'm going to do this with the function first, and then I'm going to do some substitution here. But I want you to know that the mapping doesn't care. The mapping doesn't care about what's going on here. When I compare the old function, the x minus 1 and absolute values minus 4, to the new one, the difference here is that I'm multiplying the y coordinate by 1/3. That's it. I can identify that immediately. Now let's go back, and talk about the equation. So I'm going to replace, so I've got this y equals f of x. That's the function up above it. I'm going to replace y with 3y. And now I'm going to isolate the y. So I'm going to get 1/3 f of x. Now, what I tend to see students do is this, which is incorrect. Okay? And it's incorrect because I was multiplying the f of x by 1/3. And when I did the substitution, now I'm multiplying just the absolute value of x minus 1 by 1/3, not the negative 4. I need parentheses for this to work properly. It needs to be the whole function that I'm multiplying. And then what you might do is distribute that 1/3 through. And so you get that as your expression right there. When it comes to the horizontal transformation, we're going to stretch this by about the y-axis by a factor of 2. I'm going to replace x. And if it's going to be by a factor of 2, I'm going to replace it by 1/2 x, which again means I know right away before I do anything that this is going to be, the mapping is going to be x comma y goes to 2x comma y. But now let's watch what goes on in the function here. So again, I'm going to do this to the function first. So here's my original function. Now all of a sudden it's going to be 1/2 x. And so remember, this is how you do this. So here's my function, y equals the absolute value of x minus 1 minus 4. I am going to take that x right there and I'm going to replace it with 1/2 x. Now, that's actually fine. There's nothing really wrong with that. However, I want you to get used to the idea right off the bat here before we kind of move on to where you're really going to see this pop up. I want you to get used to the fact that when you've got this binomial inside the function like this, like you're seeing with the absolute value, I want you to factor out that leading coefficient, okay? And when you take that 1/2 out of that negative 2, you're going to have negative 1. Sorry, I said negative 2 because I'm anticipating where this is going. Sorry. When I factor out the 1/2 from that negative 1, it's going to be negative 1 divided by 1/2. I multiply by the reciprocal, and I'll get x minus 2. That's where we want you to take it. Okay, we want you to get to that point right there while you're doing your work here. Okay, for this next question, it says, if the original point, 12, negative 5, is on the graph of y equals f of x, Determine the coordinates of its image point under each transformation. Okay, so what's happening here is I've got a negative outside the function, so we know that's going to be a vertical change. And that's just a reflection here. So we're going to have x comma negative y. So the point 12 comma negative 5 is going to become the point 12 comma, and then the y coordinate is simply going to change signs. Now I know that you can probably come up with that a lot quicker. You might be able to just put the answer down, and that's fine. But I'm going to just walk this thing through a little bit here. Here we've got two transformations that are occurring, and I want you to see that as two transformations. You've got a horizontal reflection and a horizontal stretch here. Okay. My image point is going to be the negative and then 1/4 x comma y. And so 12 comma negative 5 is going to become, well, the negative 5. The y coordinate stays the same. But now I'm going to multiply that 12 by negative 1/4, and I'll get negative 3. And then over here, I've got two transformations. I've got a vertical stretch and the horizontal stretch. But I got to be careful about this, and this is where we sometimes get a little bit confused here. Notice that the vertical stretch, is not on the y. It has already been moved over. So what that means is that is by a factor of 2. However, we don't isolate x. So what I'm seeing in front of the x is the reciprocal of what I want. So this is going to be 3x comma 2y. And so my point 12 comma negative 5 is going to become, I'll multiply the 12 by 3, so 36. And then 2 times that negative 5 will be negative 10. And there's my new point. Good. And that's all we have to do. Now what we're going to do is we're going to take a look at a couple of graphs here. So given the graph of y equals f of x, and notice that this isn't a nice, simple, straightforward function. It looks like a couple of absolute values kind of squished together there. We're going to sketch the graph of y equals f of negative 2x. And so what we're seeing here, and I don't have a lot of room for this, so I'll just do it real quick. Horizontal reflection, and then we've got a horizontal stretch by a factor of 1/2. Now, in the original graph that I'm looking at here, my domain is going to be from negative 6 out to positive 6. And my range is from 0 up to 4. Now, when I change these points here, basically what this means, my mapping, and I'm going to use my mapping here to help me out here. Basically, I'm going to take and I'm going to multiply my x coordinates by negative 1/2, but my y coordinates are going to stay the same. And actually, that's an indication to me right away here that I know my new range is going to be still from 0 to 4. Nothing's going to change there. But now when I take a look, and I'll switch colors here. When I take a look at my graph here, the point negative, and I'm going to go left to right here. So the point negative 6 comma 4 is going to become, well, what's negative 6 times negative 1/2? Positive 3. So it's going to become the point 3 positive 4. So this point jumps to there. Negative 2, 0. Okay, that first x-intercept there, when I multiply that by negative 1/2 becomes positive 1, 0. So that point jumps to there. The point 0, 2, well, when I multiply 0 by negative 1/2, nothing changes. So that point right there stays invariant. Now I can come over here and write that. That's the point 0, comma 2. That's going to stay invariant. But now you're probably seeing some symmetry here. And so now you'll see that that point 2, 0 is going to become negative 2, 0. And the point 6, 4 is going to become negative 3, 4. So now, when I sketch that, this is what I'm getting. And my new domain, when I read that left to right, is going to be negative 3 up to positive 3. Okay. And that's what the questions are asking for. So it helps to have the little graph there. Now let's take a look at this one. What transformations are taking place here? Well, the 5 in front has already been moved over. It has been moved off of the y. It's multiplied by f of x, and f of x represents the old function here. So it's 5 times x. So what I'm seeing here is a vertical stretch by a factor of, and I'm running out of room here, so I'm just going to say by a factor of 5. And then I've got a horizontal stretch by a factor of, in this case, because I don't isolate the x there, I have to know that implies that 1/3. Okay? So now my domain for this particular graph looks to be 0 out to 12. And then my range is going to be, looks like, negative 1 up to 1. Now in my mapping, x comma y, I am going to multiply my x here by 1/3, and I'm going to multiply my y by 5. So here we go. So let's take a look at the points left to right here. 0, 0. When I multiply that by 1/3, multiply that by 5, nothing. That's my invariant point. Nothing changed there. But if I go to the point, what have we got here? 3, comma 1. 3 divided by 3 is going to be 1. And then the y coordinate is 1. It gets multiplied by 5. So that's going to actually go up to here. The point 6, comma 0. Well, 1/3 of 6 is 2. And 5 times 0 is just going to be 0. So that's just going to go 2, comma 0. So it's going to go right here. So you can already see this is actually pulling really, really close to the x-axis. To the y-axis, and then it's moving away from the x-axis here. The point 9, comma negative 1, 1/3 of 9 is going to be 3, and then negative 1 times 5 is negative 5, so it's going to go down there. And then when I put the point 12, 0 through, I'm going to get the point 4, comma 0. So when I draw that out, yeah, I'm getting a graph that's a lot closer to the y-axis and then a little spread out from the x-axis here. So my new domain is going to be from 0 up to 4, and my new range is negative 5 out to 5. Okay, and that's what that's going to look like. So now in this next question, it says the domain of f of x is negative 4 to 8 inclusive, and the range is negative 6 to 12 inclusive. We're going to determine the domain and range of this function right here. Well, what I really got to notice here is what are the stretches here? So there has been a vertical stretch, okay, by a factor of 1/3. And I can see that because it's been moved over to the function. F of x represents the old function, so my old y coordinates are being multiplied by 1/3. There has also been a horizontal stretch by a factor of 2. And bear in mind, we're not exactly seeing that factor of 2. That's because we don't typically isolate x. Now, but what that means is for my domain, okay, what I'm going to do with those numbers in my domain is I'm going to multiply those by 2. So instead of negative 4 to 8, it's going to be negative 8 out to 16, where x is an element of the reals. For my range, it's the y coordinate, and the y coordinate is going to be multiplied by 1/3. So instead of negative 6 to 12, I'm going to get negative 2, whoops, not x, y, negative 2 out to 4. And again, I did the x there. That's weird. Where y is an element of the reals. Yeah. So we're just dividing those two by. I think I said that we were dividing the range by 2. We're actually dividing by 3. Okay. Let's move on. For each of the following, we want to go from the graph of f of x to g of x, and we want to identify if there has been a stretch or a reflection here. So for this first one here, I think it's probably pretty obvious immediately that to go from f to g, first of all, there has been a horizontal reflection. In other words, I've replaced x with negative x. Additionally, if you just compare it here, like notice this little section right here is 1 unit wide, but over here it's 2 units wide. Okay, even same thing here. This is 1 unit wide, this is 2 units wide. So there's been a horizontal stretch by a factor of 2, which means we replaced x with 1/2 x. So in my new function, I'm going to get y is equal to f of, well, first of all, there's been a negative there, and then there's a 1/2 in there. And there we go. Now this one right here, this is one that I would typically get students to try on their own, and then we would talk about together. And it's because there's actually a couple ways you can visualize this. On one hand, you might see something like this happening. To go from f to g, you might be seeing this point right here jumping up to that point right there. So this distance here vertically, this distance right here is 1, but then when you stretch it, it now goes up to 3, which indicates a vertical stretch by a factor of 3, which means I could have been replacing y with, now watch for it, 1/3 y. So that what I get here is instead of y equals f of x, okay, and in this case, the f of x is the absolute value of x, I get 1/3 y equals the absolute value of x, or y equals 3 times the absolute value of x. I'm going to come back to that in a second here. Or you might see it as something more like this. Let's say you're looking at, like, let's say this point right here, and that's, I'm grabbing that one because I've already written on this, and it's maybe a little bit clearer way up here. This point drops down and becomes to this point. So the distance from here to here was, what is that? That was going to be 12, and now it goes to 4, which indicates a horizontal stretch by a factor of 1/3. Oops. So in other words, I was replacing x with 3x. So y is equal to f of x, which is the absolute value of x, became y is equal to the absolute value of 3x. And notice that these two really are the same thing. If my coefficient there is positive, I can move that 3 inside the absolute value, and I don't really change anything. So yeah, there we go. It doesn't really matter which one of those you choose because they're algebraically identical. Now, where the points move is different, but the result is going to be the same. I like that one. That's a neat one. Here, I think it's probably pretty clear. The x-coordinate here is 6. The x-coordinate here is 2. That is a horizontal stretch by a factor of 1/3, meaning that I've replaced x with 3x. And so y is equal to f of 3x. Okay? And then finally here, let's take a quick look at this one here. The graph of f of x is equal to x plus 2 squared plus 1 has been transformed to g of x by a vertical stretch. If the point 339 is on the graph, determine the value of the vertical stretch. Here is another question that I think is worth looking at on your own before I walk you through it. So again, if you wanted to pause here, have a go at it, see what you think, and then come back here. When I answer this, what I'm going to do with this one here is I'm going to do this one in terms of the function first here. So g of x is f of x with a transformation. There's a vertical stretch here, okay? So g of x is going to be f of x with a vertical stretch here. The vertical stretch goes in front. Okay. After all that we've done with it, I hope that that's clear. That stretch is going to go in front here. Now what I would do is I can go one step further with this because I do know what the function f of x is. It's x plus 2 squared plus 1. But if I write it like this is incorrect because f of x is that whole expression here. So when I multiply f of x by a, I should be multiplying the whole thing by a. And that is not what I did. I need to put parentheses around that whole thing to be multiplying the whole thing by a. But now I have an expression for g. Okay, the only thing I'm missing is that vertical stretch. However, the question also gives me a point. I know that if I replace x with 3, that the resulting y-coordinate, which is my g of x, is going to be 39. Now this just becomes an evaluation. 3 plus 2 is 5, squared is 25, times plus 1 is 26. And when I divide and simplify, I get that my stretch factor here is going to be 3/2. That's my vertical stretch factor. I hope that helps.